Hello everyone, it's Professor Capuano again, and I am here to talk to you about Lab 9 on LR and RLC circuits. So what we're going to be doing this week is we are going to be adding a new circuit element, an inductor, into circuits with a resistor and then into a circuit with a resistor and a capacitor. Most of our work is going to be on the LR circuit, and the RLC circuit is going to just be more qualitative. So let's get started by talking about inductors and inductance and what that means. So an inductor is a coil of wire that adds inductance to a circuit. If we have an ideal inductor, then that means that we're assuming that the coil is made from ideal wire, and we're going to see why that's important in a minute. Now, what we have is self-inductance, and this is going to be an application of Faraday's law that's different from the one that we did last week. Now, in the last lab, we had two Helmholtz coils that were connected to a power supply with an alternating current, and they were creating a magnetic field that changed in time. We took a separate coil that wasn't connected to any power supply, and we put it in between those coils so that their field passed through it. And the field from the external coils created a changing flux in our secondary coil, which induced an EMF and a current in that secondary coil. So the induction came from an applied field due to another source in a coil that didn't have any power connected to it. Now, what we're going to look at with an inductor is we're going to look at a coil that has a current flowing through it. If you remember the shape of magnetic field lines, they form closed loops that go around a wire. And so when you have a coil of wire, you have a magnetic field of that coil passes through it. So the wire, if it's carrying a current, will create a flux through itself. If I then change the current that passes through my coil, I'm creating a changing flux through the coil, and Faraday's law tells us that there will be an induced EMF. So this is a different situation than what we saw last week. We have a current flowing in our coil, and what we're going to do is we're going to have an induced current in the same coil that already has current in it. And the way that this manifests itself is in our inductor resisting changes to the current in the circuit. So let's look at how the inductor behaves. It is going to be entirely dependent on what's happening with the current. So if I have a steady current, then my inductor is just going to act like an ideal wire. That means that the potential difference across it is going to be zero, and it may as well not even be there. But if the current is changing, then the inductor will oppose the change in current, and it will have a voltage across it that is equal to negative L di dt. So the di dt, that's your change in current. The minus sign is the opposing part, and the L is the inductance of the coil. So inductance is the thing where we measure how our inductor behaves in the circuit. So it has the symbol L, and it depends on the physical properties of your coil. How many turns does it have? How long is it? And what's its cross-sectional area? So the inductance was defined in a manner very similar to capacitance, and it's the same sort of idea. It gives you an idea of the behavior of this circuit element. So the unit of inductance is the Henry, and it has a symbol capital H. The voltage will be positive or negative. So does it go uphill or downhill as I travel through it? That's going to depend on what's happening with the current. If the IDT is positive, then delta V will be negative. But if the IDT is negative, that means my current in my circuit is decreasing, then the voltage across my inductor will be positive. If the IDT is zero, that means I have a steady current, then delta V is going to be zero, as I mentioned earlier. So what we're going to do in this lab is connect an inductor and a resistor to a power supply that outputs a square wave. So what's going to happen? Well, let's say for the sake of argument, we don't have an inductor in the circuit. The positive square wave means that my power supply is going to be at zero, and then it's going to turn on to 4 volts, and it's going to supply a steady current, and then it's going to shut off, and then it'll come on and off. And so it stays on each time for a brief period of time. And while it's on, the current is steady. So if I have the resistor by itself with the power supply, then the voltage of the resistor is going to match the power supply. And this is from the loop rule that tells me that if there's only one thing by itself, like the resistor alone, then its voltage has to be equal to the power supply's voltage. In fact, if I were to graph these two, I would get two graphs that matched each other. If I wanted to know what was happening with the current, I could use Ohm's law, and I could calculate it using V equals IR, and it would be a constant because the power supply was providing a constant current. So what happens if I add now the inductor? So my power supply is going to do the same thing. It'll turn on, supply a brief current, that'll be nice and steady, and then it'll turn off, and then after a fixed amount of time, it'll turn back on. The inductor does not like change. So I'm going to start at 0 volts, and when I flip the switch and turn it on, the inductor is going to resist that change. It's going to have a voltage across it, and then when I turn the current off, it will also resist that change, and there will be a voltage across my inductor. In the steady state, my inductor should have 0 volts across it. And by steady state, I mean that brief time in the middle when my power supply is neither turning on nor turning off. The presence of the inductor and the fact that it will, for brief periods of time, have a voltage across it is going to change the behavior of the resistor voltage. So now, instead of the resistor immediately jumping up to have a voltage that matches the power supply, it instead has to share voltage with the inductor. And so it will slowly build up. And then when you get to steady state, the inductor will have no voltage across it, and the resistor will have its maximum voltage. Then it will switch off, and when it switches off, the inductor will again have a high voltage across it, and the resistor will lose volts. So what's going to happen is you're going to end up with a time-dependent current due to the inductor reacting to the changes. And so this is going to change the shape of everything in our circuit. The shape it's going to have is a familiar one because it's going to cause an exponential growth and an exponential decay. And so it's going to look very similar to what we saw when we looked at RC circuits in lab. We can write the current, it's going to be a function of time, and these two expressions will describe it, and which one you use depends on which part of the process you're in. So there will be an exponential growth or an exponential decay, depending on whether your power supply is turning on or turning off. Notice that we have a tau up here in our exponential. That's the time constant, just like we saw with the RC circuit, but this time it's going to depend on the inductor and the resistor. And so we define the time constant for an LR circuit as tau equals L over R. And so if you do the dimensional analysis, you'll see that if I take a Henry and divide it by an ohm, everything will cancel out and I end up with seconds, so it is a time. And just like with the RC circuit, this time constant is the thing that is going to tell us what the rate of growth and the rate of decay are. And also, as with the RC circuit, if we want to calculate the time constant, we need to have the total inductance and the total resistance in our circuit. So what you guys are going to do is you will do some calculations involving the LR circuit, and you'll see this behavior in the graphs. Now, before I go, I want to mention two quick things that I know that give people problems in this lab. The first one is that on the second page of the lab, there's a table for you to fill out. In the first column, it is going to say the driving voltage, and it's going to say either V sub 0 or 0. So that's the on and off state. The second column is the functions for the current, and it's going to be the two functions that I have here on this slide. One of them in the on state, the other one for the off state. Then in the third and fourth columns, it asks you to write expressions for the resistor and inductor voltage. So what you guys are going to do is you have expressions for the current as a function of time in each of these states. So if I want to find the resistor voltage, if I know the current, Ohm's law is a straightforward way to get it. It's a simple calculation, so you don't have to do anything fancy. So you're just going to say V equals IR. What's your expression for I? That will give you your time-dependent expression for V. For the inductor, you have to use the expression from the first page of the lab manual, and that was on my earlier slide, that V equals negative L di dt. And so if I have an expression for the current, and I want to find out the voltage as a function of time, I have to differentiate. So you will take the derivative of the current expressions and then multiply it by the L, and don't forget the minus sign, to get the inductor voltage. So that's what you guys are supposed to be doing to fill in that table, and there's space to make sure you show your work. The other thing I wanted to mention really quick is that one of the questions is going to ask you later on, it's going to ask you how long it takes for some voltage to decay to some percent. The process for problem solving there is just like for RC circuits. And so if you know how to solve that problem for an RC circuit, you can use the same process and then the expressions that you found in the lab to calculate it for the inductor circuit. So I think that that should be everything to get you guys ready to do this week's lab. And you can look at the experiment videos so that you can see what is happening. And as usual, as always, if you have any questions, you can email your lab instructor or go to the office hours and they'll help you out.